Thank you for having me. Tonight I want to talk about an accidental discovery I made a number of years ago. I've called the talk the Zebra Stripes, and it's a new theory on animal vision, and hopefully in the next 20 minutes I'm going to change the way you understand what you see and certainly how your pets see the world as well. Can I just get a show of hands? How many people have cats and dogs in the room? Okay. So hopefully by the time you get home, you'll start doing the same kind of experiments that I did on my cat and dog. The first thing about vision is that it's really nature's tour de force in terms of sophistication and complexity. It's such an important sense that we've actually evolved this independently in the last 4 billion years, at least twice. And one thing to understand is that vision is really a function of the brain, and it has very little to do with our eyes. It's a construct of our brain, and it's our brain making an attempt to create a model of the real world. If you look at this Adelson illusion, have a look at the squares marked A and B. They're very clearly different shades of gray. In fact, they're identical shades. Now I'm going to flip back and forth, and if you pay attention to those two squares, you'll see that they're actually exactly the same shade of gray. Now the question is, what's going on here? Even if you know that these squares are the same shade, your brain is telling you very powerfully that they're very different. And this is probably the best illustration of how our brains really screw with us when it tries to create a model of reality. In order to process modern human vision the way we have a gargantuan brain, at least compared to most animals. It's something like 30 times bigger than a cat and thousands of times bigger than a fly. About 40% of our brain matter is dedicated just to processing vision. So think about this, that half of that huge brain does nothing but create this model of the real world. And the question arises is, if we can see so well with such a big brain, how does a cat or a mouse or even a fly manage to navigate, move around the world, and fundamentally, what do they see? They cannot possibly see the same things as we do because they only have a fraction of the processing power. So the question that comes in is, what do animals give up in their vision? It's not such an easy thing to determine, because if we go through the list very quickly, one of the first things is, do they maybe see in a much lower resolution than we do? And studies have shown that actually animals can see much smaller detail than we can, so we know it's not that. Color vision, now there's a slight savings in color vision. Human beings can see very well across the entire spectrum. Cats and dogs have a truncated version of that. Snakes see very well in the red, in fact all the way into the infrared. They can actually see body heat. And birds, depending on the species, have a pretty good range of vision as well, although it's mostly in the green area of the spectrum. Not much of a savings there. Is it possible that we actually see more when we look around? And we find that that's not the case. Most animals, in fact, like the horse and the fly, can see almost 360 degrees. Could it be that they're giving up depth perception? This dog certainly gave it up, but virtually every animal that has two eyes can see very well in 3 dimensions, so there's really no brain overhead savings right there. We know that predators can see in the dark way better than us, and this is a little complicated. This is something called flicker fusion rate, and it's a function of vision. The best way to understand it is to think of a movie. Human beings see at 30 frames a second, which is why we can actually watch Hollywood movies. Predators, like cats and dogs, see at 70 frames a second. And this, incidentally, is why your cat and dog are not that interested in watching TV. Their brains can't process the 30 frames a second that we can. And the housefly can see 300 frames a second. Now, this leads one to believe that if data is coming in at 300 times every second, there's a lot more data to process. So once again, this seems like they're actually doing a better job with vision than we are. Now I want to talk to you about an incident that happened to me about 5-6 years ago. I was working on some forensic video processing. It was about 3 in the morning, and I had filmed something on the table, and ran it through my forensic software, expecting a certain result, and I got something completely unexpected. I had made a bug in the software. And what I had done was I had videotaped a ruler being pulled along the table by a piece of string. So I ran this video through my software, and this is the result that I got. I had no idea what was going on, but on a hunch, I took that same ruler and I put black tape about an inch apart along the whole ruler and ran it through the system again. And this is what I got instead. This was actually very telling, and I started to develop more and more pieces of software to really understand it. Just so you know what's going on, I call this delta processing. What the software was doing was looking at each individual frame as it came through the system. Where a pixel had changed value, it rendered it on the screen, as you can see below. If nothing changed from frame to frame, nothing was rendered. So you can see the tail shows up, and that little green thing behind the tail is actually the grass, because the grass is also changing from frame to frame as the tail covers it. So this led me to a hypothesis. I believe that animals actually can see nothing. Your dog and cat are fundamentally blind, except to changes in the visual field. It's quite a radical idea, and by the time we're done, I think I'm going to change your mind, and you'll look at your animals through this light as well. This is a frame from a video that I shot back in California from the perspective of a seagull sitting on my roof. This is actually a very complex visual field. You'll notice that there's 4 groups of people, there's trees, there's lens flare, there's this funky concrete, trash cans. From the seagull's point of view, however, this is what that same scene would look like. Everything disappears with the exception of the individual items that are moving. And not only that, but the objects in the scene that are most important to the survival of the bird, such as that woman walking very fast close to the bird, or those people walking towards it a little more slowly, are rendered a lot more heavily than anything else in the scene. In fact, if you look at those people in the top right, they don't even show up to the seagull. And from the seagull's perspective, it doesn't care about those people. They're not threatening it, they're not moving towards it. So its tiny brain can easily find the shapes involved and make decisions as to whether to fly away or to maybe go and get some food. But there was a problem. And initially when I did this, I noticed that I would get results like this. And this is caused by me hold-handing the camera. So when you hand-hold the camera, you get a lot of shake. And so that means that every pixel in every frame starts to change. So I thought, well, gosh, I wonder if nature has a way that it gets around this problem. And have a look at this video, especially the hand on the left. It's being moved in a horizontal axis, and he's going to do it up and down as well. Watch its eyes, how well fixated they are, even though the movement's going on. It turns out that this behavior with cats, you can pick up your cat, you can kind of do the same thing. But it's not just cats and birds. Human beings can do it. We can read a newspaper in a car. Even the very fine print as the car is bouncing up and down. We have this ability to subconsciously stabilize our visual field. Some researchers attached these sensors to a fly's head as it sort of zipped around the room doing loop-to-loops and landing upside down on the ceiling. And they found that the fly was able to almost instantaneously stabilize its head on a specific point in the direction it was moving. And of course we are familiar with predatorial motion. These cheetahs can run at 60 miles an hour. And as they run, their heads are fixated above a certain point on the ground. Now that you're starting to think like an animal would see, flicker fusion that I'd mentioned earlier starts to make more sense. This is what a human being would see if we watch this frog leaping forward. A fly, on the other hand, within a 300th of a second, would see that outline of the frog. Whereas a dog, because its frame rate is less, would see a little more, can actually figure out what colors are involved and maybe what species of the frog. So the fact is, the faster the flicker fusion rate, the less data the brain has to process. Again, it's counterintuitive, but through the software, that explained why flies see at 300 frames a second, is actually to reduce the amount of data that the tiny brains have to process. An important aspect of animal behavior is serpentine motion. Snakes are unique amongst animals because of their particular way they move. The best way to describe it is to think of pulling a string through a curved hose pipe. Every part of the snake's body passes over the path that's laid down by its head. So it's essentially moving in its own footsteps. Why is that important? And that's because snakes are relatively defenseless animals. They have no arms or legs, and most of them aren't poisonous. Their only protection is to remain invisible throughout their entire length of motion. And they're the only animal that can actually pull this off. So we just saw this snake, this dark-looking snake rising. If we look at it through the animal vision, you'll notice that all you can see is just a portion of its head as it moves along the grass. It's very easy for a snake to hide its head, by the way. Because it's low-lying, it can hide under leaves and twigs and everything else. So fundamentally, this snake can move from A to B almost undetected by any potential predator. If, of course, we use a striped version of that snake, something else entirely different happens, and that's the snake is now suddenly rendered very clearly as if it's calling out to things to say, look at me, I'm right here. Now, why would that be? Why would some snakes hide themselves and others advertise their position? There's three basic color schemes in snakes. There's the monochromatic black-headed snake on the left, there's this longitudinal striped snake in the middle, and then the banded snake on the right. Snakes that don't want to be seen are either monochromatic or have longitudinal stripes, which do not show up in animal vision. If you look on the right, you'll see how those snakes render with those particular colorations. The only one that's visible is the coral snake. This is why I believe that juvenile and adult snakes of the same species have different coloration. The juvenile viper on the left cannot be seen in its movement, whereas the adult is clearly advertising its position to say to potential predators, you don't want to mess with me because I'll kill you. This particular cobra actually uses both. When it's moving along the ground, its monochromatic black back ensures that it's invisible, but if it wants to threaten somebody, it raises its forebody, and these highly contrasting stripes give away its position. Now, this bothered me for a while. I actually found a number of snakes, non-poisonous snakes, that were red and black stripes. And I couldn't for the life of me figure out why a non-poisonous snake would color itself that way. If we look at the snake moving across the rocks, based on everything I've said, this snake would be highly visible to a predator. Then it dawned on me that its major predator are birds, particularly raptors. And as I showed you earlier, raptors have vision that is centered around the green portion of the spectrum, which is very much like looking at the world through a green filter. When you do that, red cannot pass the green filter, so it hits the retina as black. And combined with the black stripes the snake already has, you end up with a monochromatic snake. Of course, through animal vision, the predator would see virtually nothing, again, except for the portion of the head that's crossing the ground. But why would the snake go through all this trouble to make red and black stripes? Why not just make itself black? And that's the second part of the puzzle, is that snakes' eyes are all the way to the red end of the spectrum, like looking at the world through a red filter. If you do that, red bands come up as white, and the black bands, of course, come up as black. So this snake could not be more contrasting if it tried. So from the snake's point of view, if it wants to find mates or see other mates, it's now suddenly visible to that. And if you think about this evolutionary trick, it's brilliant because you can actually move through the world invisible to the things trying to eat you, but highly visible to the dates that you're trying to make. Now, since animals can only see things that move, freezing behavior starts to make total sense. We're all familiar with these deer freezing in headlights. Some animals take it to extremes, like the possum playing dead. And even human beings have something called tonic immobility. If we're stressed, certainly if we're walking through the forest, we hear a noise, we instinctively freeze. And we take it to extremes as well with swooning behavior. The question that really comes out of this is, if animals can only see things that move, how come they don't bump into trees and walk into fences and things like that? And the answer to that is perspective changes. Now, here's a picture of 4 Obamas on the left. And if you were a dog walking through that scene, you'd notice that the chair that's closest to you changes in perspective much faster than the chairs further back. And this is just a law of physics. And it's a happy one because to the dog's cerebral cortex, the thing he has to worry about most is the thing that's rendered most heavily in its vision. And you can see as we go further back with those chairs, they render much less than the ones in the front. The chair all the way in the back is completely invisible because it hasn't moved in the animal's frame. So this is how your animal actually navigates. Think of it, can't see a damn thing, but once it starts to move, it starts to pick up these changes in its visual system. All right. Let's talk about some animal behaviors that really reinforce this hypothesis of mine. One of the enduring questions about animal behavior is, why do zebras have stripes? In order to understand this, we just look at it very quickly, the way a lion, which is the zebra's chief predator, makes its menu decisions. It's got to be very careful when it goes on a hunt. I mean, it's a dangerous thing. It doesn't want to waste energy trying to catch something that's too fast for it. So it does this little risk-reward calculation every time. That carcass on the left, it says to itself, okay, there's some nutrition there, there's no injury risk, and I've got a 100% chance of getting to it because it's not going to run away. The buffalo, on the other hand, that is a huge piece of calorie intake. It'll feed my pride for a week. The problem is it has a very high risk of injury. So it's constantly weighing this risk-reward thing as it makes a choice. The nature of the zebra, on the other hand, it's the only ungulate that will use its teeth in defense. It delivers a nasty bite, which can actually turn septic and kill you. Its hooves can shatter a lion's jaw, and it outweighs a lion, it can run faster than a lion, and it's got a really nasty temper. So now, we've got a lion taking a look at a zebra herd. In this case, there's 4 zebra. Based on what I said earlier, the lion has to be very careful to make the right menu selection, preferably a weak and diseased animal. Let's look what happens when it starts its charge. In this case, it's picked the weak animal and it fixates its gaze on that, begins its charge in this very chaotic scene. The zebra running, there's dust flying, there's hooves everywhere, and yet the lion can still pick out the individual zebra's shape and keep a lock on it. As opposed to, let's say, horses, which are monochromatic, picks the horse in second place, that same charge happens, and because of the monochromatic hide, the chosen one disappears. So the question is, why do zebras give away their position and say those deer on the right don't? The reason is that the lion will always pick the weakest, most diseased zebra, but will always pick the most healthy animal, because that's where the calories are, with the deer. So the deer want to disrupt the lion's visual system. Now that you see the world through this view, you start seeing everything in terms of new animal behaviors. If you look at this video of a stallion, zebra on the right and a female on the left, they're both standing still, but only the zebra is wagging its tail. We know that zebras wag their tails when they're angry. If you look at it through animal vision, what you see is there's no female visible, and all of a sudden you sort of see this rump being painted by the movement of its tail. And that's the business end of the zebra. If you're going to attack a zebra, that's what's going to kill you. Its hind legs. And it's not because stripes make your ass look big. In wild dogs, you have the dingo, the wolf, and the African wild dog. If you look at their tails, they're all extra bushy, and each of them have a contrasting tip on the edge of their tail, the visual signal. All right, so very quickly, other animal behaviors. This is a very common one. It's head cocking. We all do it. Virtually every animal on the planet does it, and the question is why. If you look at the graphics on the left, if an animal were to encounter something like that in nature and wanted to discern what it was looking at, one way to do it is to move the heads left to right or up and down. But through the delta processing, you can see that they don't really generate the same images that you're seeing on the left. The only way to do it is to cock your head. So this 45-degree rotation is the only thing that can actually visually get the horizontals and the verticals in a scene. And this is why, if you want to see people cock their heads, just have them look at a painting that kind of doesn't make sense. And we don't really know why we do it, but we do it anyway. Just a quick word of warning. It's a bad idea. And finally, there is some experimental evidence to support this. This was an experiment done in the 1950s by Dr. Pritchard. He attached a projector onto the surface of a woman's eye and projected directly onto her retina. And she reported seeing this little dog being projected on her eye, but after 2 seconds, the image disappeared completely. Evidence that our own visual system works in the same way. So finally, there's so many observations of behavior that start to make sense when you view it in the slide. And I really want to thank you for listening to this. I hope I've changed your minds. And if there's any questions that you have, or maybe want to email me later and discuss some of your ideas or some things that you think could help the theory, I would really appreciate hearing from you. Thank you very much.